In mathematics, and especially differential topology and singularity theory, the Eisenbud-Levine-Khimshiashvili signature formula gives a way of computing the Poincare-Hopf index of a real, analytic vector field at an algebraically isolated singularity. It is named after David Eisenbud, Harold Levine, and George Khimshiashvili. Intuitively, the index of a vector field near a zero is the number of times the vector field wraps around the sphere. Because analytic vector fields have a rich algebraic structure, the techniques of commutative algebra can be brought to bear to compute their index. The signature formula expresses the index of an analytic vector field in terms of the signature of a certain quadratic form. Nomenclature. Consider the n-dimensional space Rn. Assume that Rn has some fixed coordinate system, and write x for a point in Rn, where x equals x1, xn. Let x be a vector field on Rn. For 1 kn there exist functions phi Rn are such that one may express x as x equals f 1 x x 1 plus f n x x n. Display style x equals f underscore 1 math BF x frac partial x underscore 1 plus CDOTS plus f underscore n math BF x frac partial x underscore n. To say that x is an analytic vector field means that each of the functions phi Rn is an analytic function. One says that x is singular at a point P in Rn, or that P is a singular point of x if x P. Topic 0, i.e., x vanishes at P. In terms of the functions phi Rn it means that phi P 0 for all 1 kn. A singular point P of x is called isolated, or that P is an isolated singularity of x if x P equals 0 and there exists an open neighborhood URN, containing P, such that x q does not equal 0 for all q in U, different from P. An isolated singularity of x is called algebraically isolated if, when considered over the complex domain, it remains isolated, since the Poincare-Hopf index at a point is a purely local invariant cf. Poincare-Hopf theorem. One may restrict one's study to that of germs. Assume that each of the phi from above are function germs, i.e. phi Rn 0 r 0. In turn, one may call x a vector field germ. Topic: Construction. Let n 0 denote the ring of analytic function germs Rn 0 r 0. Assume that X is a vector field germ of the form X equals F 1 X X 1 plus F n X X n. Display style x equals f underscore 1 math BF x frac partial x underscore 1 plus CDOTS plus f underscore n math BF x frac partial x underscore n, with an algebraically isolated singularity at 0. Where, as mentioned above, each of the phi are function germs Rn 0 r 0. Denote by Ix the ideal generated by the phi, i.e. Ix equals 1 gilder Fane. Then one considers the local algebra Bx given by the quotient B x equals a n 0 I x. Display style b underscore x equals a underscore n 0 I underscore x. The Eisenbud-Levine-Khimshiashvili signature formula states that the index of the vector field x at 0 is given by the signature of a certain non-degenerate bilinear form, to be defined below. On the local algebra Bx, the dimension of Bx is finite if and only if the complexification of x has an isolated singularity at 0 in Cn, i.e. x has an algebraically isolated singularity at 0 in Rn. In this case, Bx will be a finite-dimensional, real algebra. Definition of the bilinear form. Using the analytic components of X, one defines another analytic germ f, Rn, 0, given by f x equals f 1 x f n x. Display style f math BF x equals f underscore 1 math BF x L dots f underscore n math BF x for all x element of Rn. Let Jf element of n 0 denote the determinant of the Jacobian matrix of F with respect to the basis x1, xn. Finally, let Jf element of Bx denote the equivalence class of Jf modulo Ix. Using to denote multiplication in Bx1 is able to define a non-degenerate bilinear form beta as follows: beta b x times b x b x r beta g h equals g h. Display style beta b underscore x times b underscore x stackra asterisk long right arrow b underscore x stackra l long right arrow math bound r beta g h equals l g asterisk h, where display style script style l is any linear function such that j f greater than 0. Display style L left J underscore F right greater than 0. As mentioned, the signature of beta is exactly the signature of x at 0. Topic example. Consider the case n equals 2 of a vector field on the plane. Consider the case where x is given by x equals x 3 minus 3 x y 2 x plus 3 x 2 y minus y 3 y. Display style x equals x caret 3 minus 3 x y caret 2 frac partial x plus 3 x caret 2 y caret 3 frac partial y. Clearly x has an algebraically isolated singularity at 0 since x. Topic 0 if and only if x y equals 0. The ideal Ix is given by x3 minus 3xy2, 3x2y minus y3, and b x equals a 2 0 x 3 minus 3 x y 2 3 x 2 y minus y 3 r 1 x y x 2 x y y 2 x y 2 y 3 y 4. Display style b underscore x equals a underscore 2 0 x caret 3 minus 3 x y caret 2 3 x caret 2 y caret 3 cong mathbound r Langle 1 x y x caret 2 x y caret 2 x y caret 2 y caret 3 y caret 4 Wrangle. The first step for finding the non-degenerate, bilinear form beta is to calculate the multiplication table of Bx, reducing each entry modulo Ix. Whence direct calculation shows that Jf 9 x4 plus 2 by 2 y2 plus y4, and so Jf 24 y4. Next one assigns values for display style script style L. One may take 1 equals x equals y equals x 2 equals x y equals y 2 equals x y 2 equals y 3 equals 0 and y 4 equals 3. Display style L1 equals L x equals L y equals L x caret 2 equals L x y equals L y caret 2 equals L x y caret 2 equals L y caret 3 equals 0 text and L y caret 4 equals 3. This choice was made so that J f greater than 0. Display style script style L left J underscore f right greater than 0, as was required by the hypothesis, and to make the calculations involve integers, as opposed to fractions. Applying this to the multiplication table gives the matrix representation of the bilinear form beta with respect to the given basis 0 0 0 0 0 0 0 0 3 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 3 0 0 0 0 3 0 1 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1 0 3 0 0 0 0 1 0 0 0 0 0 0 0 0 0 3 0 0 0 0 003 0000000. Display style left begin array c 0 and 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 3 0 and 0 and 0 and 0 and 0 and 0 and 1 and 0 and 0 0 and 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 3 and 0 0 and 0 and 0 and 3 and 0 and 1 and 0 and 0 and 0 0 and 0 and 0 and 0 and 1 and 0 and 0 and 0 and 0 0 and 0 and 0 and 1 and 0 and 3 and 0 and 0 and 0 0 and 1 and 0 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 0 and 0 and 3 and 0 and 0 and 0 and 0 and 0 and 0 3 and 0 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 end array right. The eigenvalues of this matrix are -3, -3, -1, 1, 1, 2, 3, 3 and 4. There are 3 negative eigenvalues #n. Topic 3 and 6 positive eigenvalues #p. 6, meaning that the signature of beta is #p minus #n. Topic 6-3 +3. It follows that X has Poincare-Hopf index +3 at the origin. Topic: Topological verification. With this particular choice of X, it is possible to verify the Poincare-Hopf index is +3 by a direct application of the definition of Poincare-Hopf index. This is very rarely the case, and was the reason for the choice of example. If one takes polar coordinates on the plane, i.e. x r cos theta and y r sin theta, then x3 minus 3xy2. R3 cos 3 theta and 3x2y minus y3 r3 sin 3 theta. Restrict X to a circle, center 0, radius 0 g, x x x. Display style g x long mapsto frac x x. The Poincare-Hopf index of X is, by definition, the topological degree of the map G restricting X to the circle CO epsilon. For arbitrarily small epsilon, gives G theta equals cos 3 theta sin 3 theta. Display style g theta equals cos 3 theta sin 3 theta, meaning that as theta makes one rotation about the circle CO epsilon in an anti-clockwise direction, the image g theta makes 3 complete anti-clockwise rotations about the unit circle CO 1. Meaning that the topological degree of G is +3 and that the Poincare-Hopf index of X at 0 is +3.